So, one thing I want you to leave here knowing that this whole business about data voids is not true, and also the fact that we have lots of data everywhere now. In fact, they're putting a new satellite up, GPM, which is going to have a radar in space, right? We were all excited about getting the Langley Hill radar on the coast, right? So you can see offshore. Well, now we're going to have a radar in a satellite looking down, scanning the planet, so we can see everywhere, even over the oceans. So I want you to get an impression how things have changed. I mean, this is radical change. So let's have a little fun here. I mean, we have these models are getting better and better, higher and higher resolution. What does it do for you? Okay, let's make this concrete. Let's go back to 1995. This is state of the art. The NGM model. 1995, here's precipitation of the NGM model. This is my colleagues of the Weather Service. This is what they would be seeing if they were in their office, right? This is what we saw. 80-kilometer grid spacing then, back in 1995. And here's the precipitation forecast. This is for 18 December 95, 12Z in the morning, okay? And this is for 12-hour accumulation. Now, do you see any impact of the mountains there?
Nope.
None, right? 80-kilometer grid spacing, you can't resolve any of the mountains right here. This is what we had in 1995. That's not that long ago. Okay, let's go in the time machine. 2007, the 4-kilometer MM5. Okay? The Weather Service has similar resolution for their model now. Their NMM model, NMB. Anyway, can you see where we are here? Mm-hmm. There's the Washington coast. Here we're down there, okay? And you can see the windward enhancement on the windward side, the southwesterly flow. On one side of the Olympics, there's tremendously heavy precipitation, and there's the rain shadow, okay? This is why all kinds of people retire to swim. Yeah. The number one question I get from people calling into the university, from my department, people from California wanting to know whether it's true that this rain shadow exists. And it's an amazing anomaly, right? You have 160, 170 inches on this side, and you get 15 inches on that side. Okay? Pretty good. And it's a rain shadow over here. So it shows you how far we've come. That's what this resolution does for you. Well, of course, I come here, we have to talk about the Columbia Gorge, right? And I and my students have spent considerable time studying the meteorology of the Columbia Gorge and seeing what resolution does for you. And now let me sort of demonstrate this to you. I'm going to show you a series of images. This is the gorge flow simulated at 36 kilometers. Here's 12 kilometers. The shading here shows you the terrain. The solid lines are the pressure pattern, and the colors indicate temperature. In reality, this day, there was cold air in eastern Washington that went through that came right through the gorge. Okay? Well, you don't see any of the cold air at all at 36 kilometers. And in fact, the Columbia Gorge is actually a pass at 700 meters. So there's no gorge, really. I mean, basically, there's a low area of 700 meters. That's like, 2,300 feet. That's going back to 2000, okay? Then we have 12-kilometer resolution. And if you look at the winds, there's a little bit of acceleration here. It is it's starting to get a little cold air, but it's not coming through at all. You can see a little bit of high pressure trying to build its way from the gorge, but it's completely inadequate. Now, a lot of the National Weather Service models are actually this resolution right now. Our 12-kilometer model is that way. It's 4 kilometers, okay? We've run 4 kilometers since the late 1990s, 4-kilometer grid spacing. Weather Service does have 4-kilometer available, and we can see that the flow of the gorge is a little bit better, okay? You're starting to get some of the cold airs moving through. And here's 1.33 kilometers. My God, this is it. Now, I don't know if my graduate student, Justin Sharp, here is not here. But my PhD student, his PhD thesis on modeling the flow of the Columbia Gorge, and what he found is you need to get 1.33 kilometer grid space to get the flow of the gorge. And here it is, cold air going straight through. And you can get the winds accelerating through the gorge, okay? So that's what we need to do. And this is what we're capable of doing today. Right now, we're running this at the University of Washington. Oh, by the way, let's go all the way. Here's 444-meter resolution. And it does a marvelous job of getting the flow through the gorge. This was not going to be operational for a while. Okay? The younger people here, you'll see this. But it's going to be a few years before we're running half a kilometer in resolution in real time. Well, we could do it. Somebody wants to give me some computers, I could do it. Here's an example of the wind flow in the gorge at 444 meter resolution. Okay, it's just amazing. This is wind speed. The red is the higher wind speed. And what you see here is something that anybody who knows about gorge weather knows. And that when we have flow moving through the gorge from east to west, the flow is not strongest in the narrowest part of the gorge generally. It's on the end of the gorge here. It's the exit of the gorge. It's where the strongest winds are. And this is beautifully modeled by the M5 and by WRF now. So we understand this, and we can model this. So this is how far we've come. Just think about how far we've come. We have now gained the ability to forecast local weather features. I mean, 10 years ago, human beings had to do the whole thing subjectively. Now the models are gaining the ability to do this. Okay? And you can see the resolution it takes to do it. So, prediction. I'm supposed to do prediction. It's going to be like Johnny Carson. It is. There's going to be a trend, clearly, towards hyper-resolution, 1 to 2 kilometers during the next few years. And in fact, as I mentioned, it's available to some degree now. You go to the website, my department. This is 12-kilometer resolution of surface temperature. Okay, temperature 2 meters. This is classic. What's available now? This is 1.33 kilometer at the exact time. I mean, how much you look at the difference?
Picks up all the valleys.
Isn't that amazing? And you start getting the ridges and the valleys and everything. You can start getting the sound, the land-water contrast. This is what we can do. This is real time. This is available right now. You can go to, this shows you the domain run at the University of Washington twice a day, out 48 hours. I mean, I just pulled this is right on the web. This is temperature, and you can see the warm temperatures, in the lower elevations of the gorge. See that? And the Weather Service, in fact, now is experimenting with the 1.3 kilometer domain. They don't always run it around here. They can put it where they want it. And this is an example of them running it over a hurricane. Okay? So 1.3 kilometers is no longer a dream. It's becoming operationally available. So hyper-resolution is something I'm going to forecast. In fact, the forecast, the future of Northwest weather prediction, that's going to be there. Now, another interesting thing I'm going to talk about is that I've been amazed with the last few months is increasingly we're starting to see examples of forecast skill beyond a week. We're seeing skill at 1 or 2 weeks out. It wasn't that long ago that we only had forecast skill really faded out 4 or 5 days ahead of time, and then maybe a week. But now we're seeing increasing examples of forecast skill out a week to 2 weeks out. Now, I should tell you, there's a limit how far we can do this. Theoretical studies indicate that we can only forecast the weather out about 2 weeks. There's a limit to how far we can forecast because of the very nature of the atmosphere, which I'll describe in a second. But it's just amazing. Our models are getting good enough. And here's an example. This is what that a lot of us have been talking about. This is now going back to that 500 millibars, about halfway up, about 18,000 feet. And this shows you the anomaly, the difference in climatology. And it was 15 days out. It was forecasting this amazing anomaly. And if you see that bright color over there, that's a huge anomaly that's a ridge. 15 days out. Here's this is the 8-day forecast verifying the same time, okay? And here's a 1-day forecast that would be actually quite close to reality. And it actually picked it up 15 days ahead of time. And that's amazing. Now, of course, it got other things wrong. But the fact we're starting to pick stuff up, this is 2 weeks out. And almost one thing we see all the time is like we go out 7 to 10 days, we're seeing picking things up. Now, here's an example. This is from the European Center. This is a 240-hour forecast over here. This is a 24-hour forecast. This is for 500 millibar heights, which are indicated by these solid lines. This tells you how high this pressure surface is above sea level. Now, I'm not going to turn you into meteorologists, all of you, right away, but there's some places of lower heights, which are troughs, and higher heights that are ridges. Now, we use this thing over here. You will notice that some features we actually were forecasting 10 days out. Look at this ridge along the west coast. There it is. It's trough here, general trough here, general trough here. The shading indicates temperatures. You get the warming, the above normal temperatures along the southwest. Here it is over here. So we're seeing now increasingly examples. 7 to 10 days out, we're starting to see some skill. This is a big change. And we're going to see this progressively change during the next few years.